Hey guys, in this video we're going to learn about the magnetic fields produced by current carrying wires. Now specifically it's going to be just long straight wires, such as the one shown here. And the deal is the magnetic field around a wire doesn't go, like, say, towards it or away from it, but rather it kind of goes around it, which is what I'm trying to show with this diagram here. Let me give you one from your textbook, which maybe looks a little bit nicer. So they're showing a couple different ways the directions of the magnetic field around this wire, which is carrying current sort of through the plane that they're showing. One is by showing you the sort of circulation of iron filings around it. And this is a real experiment that people have done. And then, of course, here we have the compass needles, which you point in various directions around the wire, showing you that there isn't like one direction for the field, right? It's not towards it or away from it, it goes around it. Now, the result here can be summarized using another right-hand rule, which we will call the second right-hand rule for the purposes of this class, and that looks like this. Now, spend some time trying to understand exactly what they're writing here, meaning pause, read it. I will, at multiple points during this video, use my right hand to show you the direction of the field and how I get the answers that I get. But it's really important that you understand this diagram, and as part of following along, you try to do the right-hand rule as well, okay? So please get that the thumb is the current, and that your fingers curl in the direction of the magnetic field. Okay, so I think the diagram does a pretty good job of showing you that, but you will witness me doing it multiple times during the video. Now, we don't always show the wire from the side. Sometimes it's going to be shown sort of with the wire carrying the current towards you or away from you. So the dot here in the center, there it is, right? That's meaning to indicate that the current is coming towards you. If you see something like an X in the middle of it, then that's meaning that the current is going away from you. So if you have the current coming towards you, I mean, you can just imagine turning this wire. You would get magnetic field lines that go like this. Okay, all right. And if it's going away from you, you get the reverse of that, right? So sort of counterclockwise for this one, and clockwise for this one. And my right hand shows this to be true. My thumb being the current coming towards the screen, ergo out of the screen towards you, shows a counterclockwise curl for my fingers, and therefore that's the direction of those individual field lines. Now, when you need to use the right-hand rule to decide if the fields are going into the page or out of the page, most often it's going to be viewed from the side, and you're going to use your hand like this. So if I've got current going up the page following my thumb, the field everywhere to the left of it goes like my fingers, which my fingers are pointing towards you. That means that the field everywhere to the left of this wire is going to be in the out of the page direction towards you. Whereas everywhere to the right of that wire, the fields are all going to be in the into the page direction, because as you can see, that's the direction that my fingers are pointing, everywhere to the right of that wire. Of course, really the lines are going, all around it, but that's awfully hard to draw. And most of the time we're going to be concerned with directly to the left of it or directly to the right of it, in which case the directions can simply be into the page or out of the page. Now let's take a moment and get some practice here with coming up with magnetic fields using this second right-hand rule. Notice in this case there's two wires. Well, all that really means is that there's going to be two magnetic fields at each position, which will either add or subtract to give you some sort of a total. So we're first going to draw all of them, and then we'll talk about whether the fields at each position add or subtract, and you might have some guesses. To help with making things clear, wire number 1 is always going to be drawn in blue, wire number 2 is always going to be drawn in red. Now, starting right off, Wire number 1 makes a field in the straight downwards direction at point 1. Hold on, Mr. Urkel, that's too fat. Well, I'm going to do this first one for you / with you. And then after you feel like you get point 1, you should try out point 2. Now, if you're trying to figure out which direction the field goes, the first thing to do is actually to draw a straight line from the wire to the point in question. Now, I'm using a dotted line so I don't get it confused with the actual magnetic field vector I wanted to draw. The reason I draw this dotted line is because notice the magnetic field is perpendicular to it. That's one of the consequences of the right-hand rule. The whole idea is that your fingers should be pointing in a direction which is perpendicular to this line, as it's called the radial vector. That's this line here. So you can first draw that to help you determine the correct direction for the magnetic field, but then you also look at your second right-hand rule. And so here's my thumb, right, carrying current towards you, and my sort of plane of my hand is supposed to be, I didn't get it quite lined up, that's supposed to be like this radial vector here. And then my fingers point in the direction of the magnetic field, like this arrow here. Oh, it works. All right, now you line up your hand, make sure it works for you before you move on to the next one. And by the next one, I mean the field produced by wire number 2, which you will note carries a current in the into the page direction. Now the field produced by wire number 2 at that position goes up. Okay, well, let's use our second right-hand rule to try to figure out why. There's my thumb carrying current into the screen, and radial vector. I mean, you know, my hand's not quite long enough, I guess. All right, and then fingers curling in the direction of the field. So everywhere off to the left of wire number 2, it's going to make magnetic fields that go in the up the page direction. Okay, so final result, B1 points down, B2 points up. All right, let's try out point number 2. Now, this might be a great time to pause me and see if you can figure it out yourself before you play. Wire number 1, with the field pointing up the page. Right-hand rule verifies up the page is the correct direction. Wire number 2 produces a field also up the page. And right-hand rule, once again, verifies up the page. All right, now before we do point number 3, which is somewhere inside my hand down here, that one's a little bit tricky to draw. I will just warn you. And again, pause me and try it yourself. But this is where drawing the radial vector becomes extra super helpful because it matters that the magnetic field is perpendicular to that radial vector. So try and draw this one very carefully. All right, now I hope I haven't failed you at drawing 90-degree angles, but this right here, that should be 90 degrees. And so if you've drawn it well and drawn everything proportionate to my diagrams, it should look like that. And here we are verifying that result with the right-hand rule. Now, at this point, if your head is spinning with this second right-hand rule, and you're like, what in the world is even going on anyway? I thought, why are there two right-hand rules? Well, there's two right-hand rules because they are for different things. They're both a right-hand rule. In fact, there are at least 3 different right-hand rules in physics that I know of. So you need to know that this one is used for finding fields, whereas the other one that we learned is used for finding the force produced by fields. Okay, so in this one, your thumb is the current and your fingers are the field. Notice that the way I drew it, the red arrow for the red magnetic field doesn't run parallel to the blue radial vector there, right? So if we've drawn it well and to scale, this is what that picture should look like. Okay, so be very careful with the perpendicular thing. Okay, it's got to be 90 degrees. If it's not 90 degrees, then you've drawn it wrong. All right, now once again, pause me, try out point 4 on your own for a little bit before you resume the video. That's what we should get. Let's check with the right-hand rule. Wire number 1 with the up the page direction, which is to be expected because off to the left of wire number 1, it's producing fields that are directly downwards. So it should make sense, based on everything we've discussed so far, that off to the right of it, it will make a field that goes in the upwards direction. They should be opposites. And wire number 2 in the downwards direction. All right, now if you were wondering, yeah, like, so what, right? They go up, they go down, what's the big deal? Well, the big deal is that if you want to know, say, the total magnetic field at a particular point, well, you have to draw these arrows. And so if they look like this, where they're in opposite directions, that's subtraction. Okay, and so the total magnetic field would be either up or down, depending on which of those two is larger. If it looks like point 2 here, that's where they're going to add together because they're in the same direction, so you don't have to worry about is it up or down. I don't know. It's up in this case. Point 3 would be a bad day. I mean, not the worst day. You know, you could maybe do it, but we won't touch those in this video. In this video, we're going to deal with just the situations like points 1, 2, or 4. All right, guys, stay tuned for the next video in which we're going to learn about how to actually calculate a magnetic field.